again, I start something new. It's the common subject of the last 3 lectures is the following: integrable systems with spectral parameter on a Riemann surface. These systems include, in particular, Hitchina systems, Euler type systems, which already have been considered in the last 3 lectures, and let's say almost all classical integrable systems. And let me start with the notion of Lax operator with spectral parameter on a Riemann surface. But, oh, sorry. First of all, let me recall that for Euler-Arnold-Monakov equation, which was an example of Euler type equations, which we completely resolved at the last lecture, the Euler-Arnold-Monakov equation has the form of Lax equation dot L equal to commutator of Lm, where L and M expressed via 2 other operators, omega and G. Omega is a skew-symmetric matrix and of dimension n, and is called generalized angular velocity or just angular velocity, and G is the inertia tensor. Inertia tensor. Altogether, this equation is the equation of free rotation of a rigid body, fixed with one fixed point. Let me recall that L is called the Lax operator. M, I will call M an M operator, just M operator, and use the term Lm pair for this pair, L and M. Someone use the term La pairs. It's all the same. Okay, so here in this second line of relations, this lambda, which is called a spectral parameter, is involved. So omega, okay, good. And L and M are functions of this lambda, which take values in the Lie algebra of skew-symmetric matrices. Later, when I was in course of constructing of the Baker-Ahieser function for this and other equations of Euler type, I considered lambda to belong to the complement, or let's say completion of C which is P1 or Riemann sphere, or rational Riemann surface. For this reason, lambda is called rational spectral parameter, and such Lax equations are called Lax equations with rational spectral parameter. It is my aim for this lecture to generalize this notion to Lax operator with a spectral parameter belonging to an arbitrary Riemann surface. This was just introduction, and let me start. What is geometrical data which we need to define such kind of Lax operator? This geometrical data is as follows. First of all, this is a Riemann surface, which is denoted by sigma. Then, okay, on this Riemann surface, we fix n points P1 and so on Pn, and another set of points, gamma 1 and so on, gamma k. With every point, we associate an n-dimensional vector. Let's denote them alpha 1 and so on, alpha k, and alpha s is associated with gamma s. Okay, here I just sometimes I will omit number of this pair, gamma and alpha, and write them just without any index. Pairs gamma alpha are called Turing parameters due to the following theorem. Let G be a genus of our Riemann surface. N is a natural number. Then there is a one-to-one correspondence between the pairs of sets of gammas and alphas, and the equivalence classes of semi-stable holomorphic rank n vector bundles on sigma. I will not explain the meaning of this term semi-stable. For those who doesn't know, I only let me only tell that it's a bundle in a general position. A bundle in a general position. So a rank n bundle in general position can be given by such set of parameters, gamma 1 and so on, gamma and g, and alpha 1 and so on, alpha and g. Well, further on, I will not prove this theorem. It is not that easy, but I will explain why, how these parameters sorry, this is Grinevich who is calling me, deputy. лекция есть, она уже идет. Прости, Петя, прости, я просто зачитался и тебя не принял. Все, пока. So, excuse me, please, this was Petr Grinevich, who was waiting for entering the lecture. Okay, and entering the conference. Well, okay, I will explain how these parameters come from a holomorphic rank n bundle in general position. Well, by Lax operator with spectral parameter on the Riemann surface sigma, I mean a meromorphic function on sigma, which takes values in the Lie algebra G. Unfortunately, I skipped G in my explanations. So we, among other data, we also fix a classical Lie algebra G over C. So by Lax operator, we mean a meromorphic G-valued function L on sigma with arbitrary poles at P points and simple or double poles at the gamma points. L is assumed to be holomorphic at the other points and have the expansions of the following form at gamma. Let me comment. So we had a Riemann surface. Sorry, had a Riemann surface. Sigma. With two kinds of poles, P1, with two kinds of marked points. And we allow L to have arbitrary poles at P1 and so on Pn, and only poles of a prescribed form at gamma 1 and so on gamma k. Okay. Let's say that the form of this expansion depends on the Lie algebra G, over which we define our Lax operator. First of all, I said L has simple or double poles. For this reason, I start the Laroe expansion from the term of order -2. Well, and for if G is equal to GLM, by the way, what did I say? I consider only okay. I didn't specify which kind of Lie algebra I will consider. I only said it's classically algebra. I mean classical reductively algebra, which include GLN, SLN, orthogonal and symplectically algebras. The simplest expansion has have Lax operators for the Lie algebra GLN, full linear algebra. Then for it, L minus 2 is equal to 0. This term is absent. L minus 1 is of the form alpha, beta, t. Let me explain. We are at the point gamma here. It is associated with certain vector alpha, which we regard as a column alpha in Cn. Well, let beta be also n-dimensional vector. By beta t, I also will write beta t capital. It will be the same. I mean transposed vector. So if alpha was a column, beta t is just a row. Okay, and any question? Alpha beta t is the following. We multiply two matrices of such form, and what we get as a result is the following. It's quadratic, rank 1 matrix. Every column is proportional to alpha. If beta is just beta 1 and so on, beta n. Then we have here beta 1 alpha and so on. The last column is beta n alpha. So for GLN, this expansion begins with a term of the form alpha beta t divided by z plus some A0 we only require in all cases that L0 has alpha as an eigenvector with some eigenvalue k, kappa, let's say kappa. Well, so for GLN, plus something of order z. Plus something of order z. Now, for Lie algebra of skew-symmetric matrices, we take a simplest skew-symmetric matrix, which can be formed from two vectors, namely alpha beta t minus beta alpha t, and put it here. So for SON, the expansion is as follows: L of z is equal to alpha beta t plus, minus beta alpha t over z plus L0 plus also something of order z. And finally, for the symplectic Lie algebra, a term of order minus 2 emerges, and for SP of 2n, of 2n, L of z is equal to some number alpha t sigma over z squared plus alpha beta t plus beta alpha t sigma over z plus L0 plus remainder of the expansion, where sigma is the matrix of the symplectic form, say such matrix, where E is the unit matrix, unit matrix. You can observe that alpha t and alpha beta t plus beta alpha t are simplest symplectic matrices which can be formed from two vectors. For symplectic case, there is one more relation for symplectic case, but I will not write it down because I will be in general. I will be basically dealing with Gaussian case. Well, questions. Maybe let me ask for questions now. No question. Okay. Good. I must explain. Let's say I will try to explain where such form of the Lax operator comes from, why the Lax operator of the Hitchin, say of the Hitchin system, is of this form, and all such questions. As I told, I will deal with the easiest case of JLN. Nevertheless, I would like to mention one more way to define Lax operator, which is which fits for an arbitrary reductive group or Lie algebra, and in many respects simplifies the presentation. So for an to generalize this picture to an arbitrary reductive, let's say, Lie algebra, we only replace the requirement with expansions at gamma points. We only write it down in the following form. So we are at the point, we are in the neighborhood of a point gamma with a local parameter z. Let H be an integral element of the Cartan subalgebra of the Lie algebra G. Then we consider the following requirement. L of z is just holomorphic, just some holomorphic G-valued local function L with index whole, with upper index whole, conjugated by z to h. Okay. Here are two forms. If somebody, if it is more convenient to somebody to define z to h as exponent of h log z, then you can do it. It depends on your personal taste. But these two expressions are completely equivalent. Well, so for example, let me show that for G equal to full linear algebra, this condition is just the same as as to give an expansion of the form which I invented earlier. Well, so we consider full linear algebra, and we take H, a diagonal matrix with the elements -1, 0, 0.0, 0.0 on the diagonal. So H looks as follows. 1, 0, and so on. 0, 0, 0. -1, sorry. -1. Just for a moment, denote L holomorphic from 0 by A capital. And consider a joint operator corresponding to Z to H applied to L. I mean, consider this expression actually, but replace L holomorphic by A, just for simplification, the notation, simplifying the notation. We will easily obtain the following. Z-1 will appear in all elements of the first row, of the first line, except for A11. Z will appear in the first column, and all other elements do not change. Do not change. Expand this matrix in powers of Z. So for we will have the following. So at the term 1 over Z, Z minus 1, we have the following matrix. 0, something in the first line, and zeros at all other places. Well, plus the matrix of the form A11, 0, 0, and something here, plus I even will not write down all other terms because they are just O of Z. We have order, first order in Z. This matrix, this one, at the term 1 over Z, let me again, of this form is just equal to y is following. Is it clear? Is it clear? If we multiply this column by this row, we just obtain a quadratic matrix of this form. Denote it by alpha 0 and add by beta 0. And this by beta 0. So Z A 1 is equal to alpha 0 T transposed over Z plus L0. L0 is just this matrix plus O of Z. And The concluding step is the following. Concluding step is the following. Observe that Cartan subalgebra is defined up to conjugation. Let me beg your pardon for this quite inaccurate sentence, but I mean that we can consider H up to conjugation. There is so-called gauge transform. If where G is just an element of GLN. If we apply, if we operate by this conjugation on this equality, we will see that alpha 0 goes to G alpha 0, beta 0 goes to beta GT minus 1, and also L0 goes to some matrix and so on. Under this conjugation, alpha 0 can be taken to an arbitrary vector. And finally, we obtain, after conjugation, we obtain an arbitrary vector here. And we exactly obtain the form, we exactly obtain the expansion for L, which I postulated here for JLN. Let me think that I convinced you that everything which I will tell in this lecture, I'm able to generalize on an arbitrary reductive group and just forget about all groups except for full linear group and focus on this on this case. Please, questions at this point.
Sorry, may I ask a question?
Yes.
So maybe naive. So you mentioned that at a certain point, like gamma, the function have at most poles of order at most 2.
Yes.
But here you choose H diagonal matrices. Do you have any restriction on the terms in these matrices? For example, if you have -10 or something like that, you will get poles of order higher than 2.
You mean by diagonal? You mean H?
Yeah, H, right?
Yeah, it should be Cartan, an element of Cartan subalgebra. For example, for symplectic and orthogonal case, it is of the form H1 and so on, Hn. Sorry.
Yeah, I see you somehow choose an element in the Cartan subalgebra, right?
Yeah. First of all, the trace for semi-simple algebra, the case, the trace should be equal to 0.
0.
And
Yeah.
moreover, for symplectic, it should be H1 and so on, Hn minus H1 minus Hn on the diagonal. Okay.
Okay.
So they are Cartan elements, and that is.
Do we need to pay attention to, for example, you choose a -1, 0, 0, but if you choose, for example, -3 or something like that, you will get the order of the pole will be higher than 2. Is that okay?
Okay. Okay. That's true. We can also consider this case. I didn't tell that these two approaches are equivalent. I only claim that this second approach includes, in some sense, the first one. But you see, we can. We must also distinguish between choices which are sensible from the point of view of integral systems or not sensible, and so on. It's what I told is only how to generalize simple things which I'm going to tell today to an arbitrary reductive, complex reductive group. Okay.
I see. Okay.
It is not completely rigorous. Not completely rigorous. How to say? No completely rigorous theories here.
Okay. Okay. I see.
It exists, but not in this lecture.
Okay. Okay. Thank you.
And the last non-obligatory remark, I should say, if we consider lax operators of the form I just postulated, then they form infinite-dimensional Lie algebras of matrix, say matrix valued function or G-valued functions on the Riemann surface. It's especially easy to see in this in the form where it's very easy to see that the form L of Z equal to Z to H L holomorphic of Z to minus H. This condition is preserved under commutator of such two operators L1 and L2, because if we take the commutator, we have just Z to H, L1 holomorphic, L2 holomorphic, Z2 minus H, and everything and this operator also satisfies this requirement. So such operators form a Lie algebra, and these Lie algebras are a direct generalization of loop algebras or Kazhmoody algebras and Krzyver-Novikov current algebras. Let's say loop algebra is just a tensor product of G by the commutative algebra of Larrault polynomials, and we obtain it when our Riemann surface is of genus 0, is a Riemann sphere with two fixed points, P1 and P1 equal to 0, P2 equal to infinity. And Krzyver-Novikov algebra is similar thing, a tensor product of G by a commutative algebra of meromorphic functions on a Riemann surface of a positive genus with certain number of fixed poles and holomorphic outside them. Okay, this is also a fact which has some consequences. I would like you to know it, but I will not tell anything. I will not tell any more about this. Okay. Any question here? Okay. So let's consider the following question: how to define a Lax equation? What we need to define a Lax equation having such a Lax operator. What we need is the second operator M, which also is required to satisfy completely the same conditions as L, except for one. We don't require that beta sigma alpha is equal to 0. Let me return a little bit. Oh, sorry. So an M operator fulfills exactly the same conditions, except for this one. Except for this one. Sorry, and oh, I don't remember, but I will not need it today, certainly, except for these two ones, I guess. Except for these two ones. Except for these two ones. So, for example, for in the GLN case, an M operator satisfies has the following expansion at a gamma point. That's alpha mu T over Z plus M0 plus and so on, with no condition of this type, and no condition this is also omitted. Just this expansion. if we give if we give L and M operators, let me ask, what will be dynamical variables of the obtained dynamical system? So dynamical variables are the following. First of all, these are alpha, beta, gamma points on the Riemann surface, and kappa. Kappa comes from the condition. Kappa comes from the condition L0 alpha is equal to kappa alpha. It's just eigenvalue of L0 on alpha. So if we consider the whole collection of points gamma and associated vectors alpha, beta, and numbers kappa, we obtain just by definition a phase space of this dynamical system. Question? No. Well, and another point of view is to consider L as an element, L as such as an element of the phase space. For example, from this equation, L equal to commutator Ln, we just using the chain rule of calculus, we can consider it as a system of equations on dot alpha, dot beta, dot gamma, dot kappa, and so on. Now let me start with examples. The first one is Algebro-Moser system. The Algebro-Moser system. I want here to just to define a Lax operator of this system. I do it as follows. The entry Lax operator or Lax matrix is given by its entries, and let me just define the entry with indices ij just by explicit formula where sigma is a Weierstrass sigma function. Sigma is a Weierstrass sigma function. Weierstrass sigma function. I will not tell what is this. Actually, I only need the following. It is a function on an elliptic curve on sigma elliptic. So we consider elliptic curve here, and it is quasi-periodic. Sorry, it's not a function on sigma. It's a function on its covering, which is quasi-periodic. And such that sigma of z is equal to sigma of z is equal to z plus here plus something, I guess, z to 5 plus and so on. Lena, correct? Is 5 here?
Yes. Yes, I think so.
It's a quasi-periodic function on the covering of the elliptic curve, having a pole, having a simple zero for z equal to 0. Z is a coordinate on the covering. Well, first, if you take any, let's say, oh, sorry, как сказать справочник по-английски? Кто мне скажет? If you take any handbook, and learn this.
Reference book, кстати. Не reference book.
Reference book or handbook, I don't know. And see these factors of quasi-periodicity there, then you will see that Lij is already well-defined function on the elliptic curve. It is actually true for every such fraction where sum of the number of occurrences of z at numerator and in the denominator are equal. So this one is well-defined function on the elliptic curve. We can check that. Chosen. Okay, on the diagonal, we put pi, which we regard as momenta, which we regard as a momenta of our system, while qi we regard as coordinates of the system. So this Lax operator describes the motion of n points q1 and qn on the torus. Sigma is the torus here, where P1, Pn are their momenta. Okay. Okay. We can first of all, let me explain why the Lax equation L point. Okay, let me explain why Hamiltonians corresponding to these Lax operators, second order Hamiltonian is the Hamiltonian of the elliptic Caligera-Moser system. Hamiltonian of the elliptic Caligera-Moser system, just by definition, is equal to this one. How to derive it from the Lax operator? To derive Hamiltonian from Lax operator, we have to consider invariance of this Lax operator. Consider an invariant of the second order. It looks like this. It's equal to trace L squared. If it is the same as sum of pi squared, it's square of diagonal plus sum of Lij I less than j. Now let's consider this product. Consider this product. If we see that we can easily see that all terms which of the form sigma of qi qj, z minus qi, z minus qj, z minus qi will cancel. What we have in remainder is the following. Sigma of z plus q j minus qi, sigma z minus qj plus qi divided by sigma of z squared, sigma of qi minus qj squared. Now there is an addition formula for the sigma function, which is as follows: sigma of u minus v, sigma of u plus v divided by sigma of u squared, sigma of v squared is equal to sigma of v minus sigma, oh, sorry. P function, Weierstrass P function of v minus Weierstrass P function of u. And for this reason, we obtain on the right hand side of this equality the following: sum, a sum of terms of the form p of qi minus qj minus p of z with some coefficient here, which is not interesting for me now. And we have to sum here minus less than j. Well, now the recipe for the prescription for Hamiltonians is the following. We should expand this invariant, this or other invariant in powers of z, and take the coefficient. They will give Hamiltonians. One of the these coefficients is, okay, consider the coefficient at z minus and z2 minus 1. That is the residue of trace L squared, residue of this at the point z equal to 0. We must multiply this this whole by 0 by z minus 1 and take a residue. A residue of p of z is equal to 0. We will have, and this stuff will give exactly the Hamiltonian of Kolazhero-Moser system. Just one moment, excuse me, please. Well, now I explained what is Lax representation of the Kolazhero-Moser system. I don't know actually whether to ask you to check that, that this is exactly the operator, the Lax operator of the form I just invented, or leave it as exercise, because checking it here, I will spend a lot of time. But okay, let me nevertheless check that this operator satisfies, has the expansions of the required form, of the form as they required for Lax operators. Well, consider L at the point QK. At the point QK. L of z, let's say, at the point QK. So consider Lij of z. If I is not equal to k, then nothing vanishes in the denominator. The denominator has no zero at the point QK. Okay, and the residue of Lij for such for I not equal to k is equal to 0. So a residue K L ij is equal to 0. We already know that the matrix of residues of the operator L is of such form. Only row number I can be non-zero, and everything other is 0. Now consider K. I should write K here. Now let E be equal to K and G not equal to K. So we consider an entry of this row except for diagonal one. Let's say we should calculate the residue of this expression when Z is Z tends to Qi, because sigma has simple zero. At the simple zero, for Z equal to Qi, to calculate the residue, we must just drop out the sigma in the denominator and just plug Z equal to Qy in the remainder. And we will see that this residue is equal to the following. Plug Qi here, we obtain sigma of Qj. Then sigma of Qi minus Qj, sigma of Qi. Plug Z equal to Qi to the denominator. This sigma is dropped out already. We obtain 1 everywhere. So all entries of this line are 1, 1, 1, except for the diagonal one. But in the diagonal one, for the diagonal one, this formula works. Not this one, but this one. But Pi doesn't depend on Z, and so the residue is just 0. We obtain a matrix with all rows equal to 0 except for the row number K, which has 0 here and 1 and so on, 1 here. And such matrix is exactly equal to 1 at the case place by this one. At least I checked that the residue of this matrix valued function is of the form I postulated, and all vectors alpha are the same. All all vectors. I mean, all vectors. Okay, these are constant vectors which have a unit at case place and zeros in all other places. Well, any question at this point? We must certainly check other conditions, but let me leave it as an exercise. I want now to explain why the Lax operator for a Hitchin system how you see how Lax operators for Hitchin systems are related to Higgs fields. I mean the following. Every integrable system can be defined by its Lax operator. I just can give the following definition for a Hitchin system. It's a Lax is a system which is given by Lax representation of the above type, where Lax operator is additionally specified by two requirements. First, its poles are located at zeros of a certain fixed galomorphic differential omega, and the number of points gamma s is equal to ng, where G is the genus of the Riemann surface. N comes from GLN. Well, it can be considered as a one of definitions of the Hitchin system. How is it related to the classical definition via Higgs field, via Higgs fields, which I started with in explaining the Hitchin systems in the beginning of this semester. I must to connect somehow this Lax operator to Higgs fields. Let me recall something of Higgs fields. We consider holomorphic bundle B with a fiber V, which is n-dimensional, given by gluing function Gij. I mean that there is a local trivialization and a gluing function which identify fibers over intersection of any two sets, open sets of this trivialization with numbers I and j. So let me recall the picture. So on the Riemann surface, we have open sets ui and uj, and a cylinder with fiber V, here, and here, and over the intersection, we identify fibers by operators Gij called gluing functions. Gij depends on P, a point of this intersection. Well, then let's do the following. Take a fiber V over some point and consider the space of endomorphisms. Of this fiber. Let's say it is the same as linear operators in the vector space V. Consider end V as a new fiber, and gluing functions with gluing functions add Gij. This means that in this new fibers, which are spaces of operators, we take the gluing function takes an operator here and conjugates it by Gij. Conjugates it by Gij, and the result is just an element of this fiber. The holomorphic bundle obtained this way is denoted or called end B. The bundle of endomorphisms of the holomorphic bundle B. You can have a look at lecture 3 and see that the definition of the Higgs field can be interpreted as follows, given there, can be interpreted in these terms, and in the particular case of G equal to GLM, or G equal to GLM, can be interpreted as follows. A Higgs field is a holomorphic section W of the bundle of endomorphisms tensored by canonical bundle. Let me recall that canonical bundle is the bundle whose sections are meromorphic differentials or one forms. So we take a section of this. We take a section of this bundle. It's called a Higgs field, but I called a Higgs field a little bit different stuff. I chose a holomorphic one form, omega, divided V by omega, and this now operator valued function phi. Now it's a function because I divided the sections of this bundle are one forms with operator values, and I divided by a scalar one form and obtained a bundle, and corresponding sections are just operator valued functions with poles at zeros, of the holomorphic differential omega. Well, sorry. Now to explain, I will just finish and only tell you what I wasn't able to tell today. To make a bridge between Higgs fields and Lax operators, I must introduce quite interesting parameterization of holomorphic bundles, which is called Turing parameterization. This alphas and gammas just are Turing parameters and describe Higgs fields. Describe Higgs fields in terms of Turing parameters. Then I will exactly obtain a Lax operator of the form I invented in the beginning. So let me stop here and go on next lecture. Well, questions, if any. No question. What I was able to tell today, let me repeat. So geometric data, which define Lax operators on a Riemann surface. Just definition of the Lax operator, possibilities of generalization to arbitrary reductive group. What is Lax equation? And the only example, Calogero-Moser system. Unfortunately, that's all for today.